Hi, today I'm going to talk about unified Ohm's law for charge and spin currents. This is sort of like a summary of several different problems um, that I talked about before. So I noticed that in all of this spin and charge transfer problems, people actually use different sets of formulas. I wonder why that's the case. So look at them together and compare them, and finally realize that there is a unified theory behind. It's just sometimes, since the cases are different, you can make simplification. So that's why you end up with different cases. Okay, so let's talk about that. So this is a reference if you want to read. So first, let's start from the very beginning. In other words, the definition of charge current. This is a slide I borrow from the electromagnetism I teach undergraduate class. Okay, so when you talk about charge current or simply electric current, you think about a lot of charges that move around, right, and go across cross-sectional area. And the charge current basically is defined as the amount of charge that goes through this cross-section for unit time. Related to that is a concept called charge current density, basically the current divided by the area. That's operational definition or microscopic understanding. The microscopic picture of this has to do with really you think about how many charge carriers or electrons are moving, right? How fast they move, and the charge each charge carrier carries. So if you put all this factor together, you actually get charge current. Here is the interesting fact that the charge carriers, when they carry charge, they actually have a lot of collision or scattering, whatever you want to call it. So although each charge carrier move, the instant speed is very fast, into the 50 meter per second, but their average speed, or in other words, called drift speed, much slower. It's like 7 or 8 order of magnitude difference between the two kinds of speed. So what governs the current? How much current can we get? This is something we're familiar with, is Ohm's law. Basically, you apply voltage, and depending on the resistance, you get a certain current. So here, current and voltage are both something that we can measure. You can also relate the voltage to electric field times the length of the conductor, and current is current density times the cross section, and put this together, and you can end up with another form of Ohm's law in terms of charge density, current density, electric field, and conductivity. Conductivity is also related to something called resistivity. Basically, they're just like inverse to each other. Okay, and conductivity, resistivity are sort of a material property. They are not related to the size or shape of the conductor. So in other words, Ohm's law in this case also is related. It's not related to the size or shape of and resistance. So this is why actually most of the time we're going to actually use this form of Ohm's law. Okay. So now let's look at the spin current. Spin current is quite similar to a charge current. Charge current is a flow of charge, right? So this is a formula we just talked about. Charge current is proportional to the charge, proportional to the density of the charge carrier, and proportional to the velocity. Spin current is similar. Spin current is not flow of charge; it's a flow of spin angular momentum. So we have a density, we have a velocity, but then we have a spin angular momentum. Because spin angular momentum is a vector, so that makes spin current sort of like tensor with two indices. So to make the theory easier to deal with, Diakonov introduced this unified definition of current. So essentially, we know charge current is flow of charge. Spin current is flow of spin angular momentum, but charge current is charge is carried by electron, right? And angular momentum is also carried by electron. So if we remove that part, we end up with something like flow of particles. Okay, so Diakonov introduced Q. Basically, the relation between Q and charge current is this factor E. So you basically just don't think about the charge, and you get this number current density. And similarly, you can do this with spin current. You also get something with the same dimension number current density, but it's a vector. So here, important concept is this in polarization P. P is a dimensionless factor. It can be less than 1. And this P, capital P, is called polarization density. Basically, it's a lowercase p times the density characteristic. Okay, so with that definition, those are all just definitions. Okay, with that definition, now we can look at a few cases, namely spin Hall effect, spin Hall magneto-resistance, and spin injection. First, let's look at spin Hall effect. Spin Hall effect basically is a typical case for spin charge conversion. So in this picture, you can see if you flow a charge current, then you generate spin current by splitting this spin up and spin down in 2 different ways. Okay, charge current go this way, and another transverse direction, spin up and spin down go opposite direction. So effectively, you actually have a transverse spin current, and you can have spin current, and that generates a transverse charge current. This is called inverse spin Hall effect. Okay, this is a 2-dimensional case that you often see. Well, what I also like to show you is this is a so-called spin Hall effect in a wire. Think about a charge current flowing into this plane. So you're actually going to generate spin current in the radial direction, and of course the spin polarization will be in the tangential direction. All right, let's come back to the formula, the mathematical description of this process. So if we look at the charge current, we have 2 terms. First term is Ohm's law, partial V pi per x, basically electric field, and this is basically conductivity. Then this is the inverse spin Hall effect. Related, of course, we have the spin Hall effect, and for spin current, we also have 2 other source. One is spin polarized current. If you have a charge carrier that are spin polarized, like you have more spin up than spin down, for example, and then it flows, then there's a spin current. And you can also have the diffusion of spin polarization. If spin polarization is different, you get some place that has more up than down, some place that have more down than up, and you'll generate diffusion and cause spin current. So, all right, so that's a spin Hall effect. Second is something related to spin Hall effect called spin Hall magneto-resistance. So this is not a bulk effect. This is an individual effect. If you look at this picture, basically, if you have a charge current flowing this direction, then you generate spin current towards the interface, and that spin current gets reflected. Okay, and the reflected spin current will generate charge current, and this reflection is going to be dependent on the magnetization of this the magnetic insulator. So by controlling magnetic polarization or magnetization of the insulator, you actually can control the reflected spin current and this charge current. This is what gives you spin Hall magneto-resistance. Okay, so let's look at the mathematical description. Here we still have four terms. The first equation describes the charge current, and it's essentially the same as what we see. This is Ohm's law, and this is inverse spin Hall effect. And the second equation describes the spin current. That looks quite different. Okay. Well, first let's look at the second term. This one is something we're familiar with, spin Hall effect. Essentially, if you have electric field that drives a charge current and it generates spin current. And this one actually looks new, but it's actually not new. It's actually exactly the same as what we just saw. It basically combines the two terms we talk about. One is the impolarized charge current. One is spin current from the spin polarization diffuse gradient. Here we introduce a new symbol called V. V0, of course, is still just the normal electric potential, but VI, I equals 1, 2, 3, basically is the so-called spin potential. The idea about spin potential is it's the equilibrium state compared to the equilibrium spin polarization. Okay? If the spin polarization is different from the equilibrium spin polarization, then the spin potential will change. That's the idea. So this essentially applies for both non-magnetic metal and ferromagnetic metal. For non-magnetic metal, you have the such as platinum, the I0 equilibrium polarization is 0. Ferromagnetic metal, that's not 0. All right, so essentially this is the same formula, but a different notation. Importantly, we introduce the concept of spin accumulation or spin potential. So now let's look at spin injection. This phenomenon is also an interfacial phenomenon. Essentially, you have a ferromagnetic metal like iron, cobalt, nickel, and a non-magnetic metal like cobalt and aluminum. And if you flow a charge current across the interface, something interesting will happen. Okay, so the charge current in the ferromagnetic metal is spin polarized, right? We know in iron you should have more spin up than spin down, for example. So when the current flow into the non-magnetic metal, so some spin polarization will be carried over into this non-magnetic metal. So we also have a little bit of a spin polarization, but that's not going to last forever. It will only last over something called spin diffusion length. Actually, the ferromagnetic side is also affected a little bit. The spin polarization over spin diffusion length also is not the same as the bulk case. It's actually reduced. So that gives you the spin current change. Okay. Far away from the interface, of course, you have no spin current in the non-magnetic metal. You have a constant spin current in the ferromagnetic metal. But in the interface, there's a gradual change. The charge current, of course, is all the same, constant, going from one material to another material. Okay, now let's look at how we describe this this phenomenon. So again, we have two equations. The first equation is the charge current, and we have the familiar Ohm's law, and this is something new. Okay, so here we introduce another concept called HJ. Actually, it's basically, or HI, it's basically VI we just introduced, I equals 1, 2, 3. It's a spin potential or spin accumulation. Okay, so let's try to understand this term by looking at this picture here. Supposedly you have in space, right? Some place you have more spin up, and some place you have more spin down. Okay, so this imbalance basically will cause diffusion, as we say. Since you have more spin up going this way and less spin down, has less population. So when they go toward each other, the total spin polarization or spin current is not going to be canceled. Okay? And of course, the total spin polarization is going to be proportional to the PJ, which is imbalance between the two arrows. If we have the same up and same down, then of course, if up and down arrow are the same, then it's totally canceled. So that's the spin diffusion. Although it's really just a great gradient of spin polarization, and that gives us charge current. Okay, and similarly, so when the we have again this change of spin potential, we have charge going this way and this charge going this way, and we have charge current. So charge current is actually not going to be affected by the spin polarization. It doesn't really matter. So so we have this spin current. So I already said charge current. So we have spin current this way and spin current that way. So actually the two current will going to have to add up. So actually we have something like this. Okay, and the first term assumption we already talked about is spin polarized current. And this one is actually the same as what we talked about, right? Diffusion because of spin polarization. Okay. So now we have everything. We can basically put everything together. So in total, we actually have 3 terms for each current. For charge current, have the Ohm's law, have inverse spin Hall effect, and we also have this this new effect that we talk about, right? Gradient of spin polarization, and overall, the charge carrier is spin polarized, and you generate a charge current. So this is only useful, or this is only significant when PJ is big enough. This is why only when you have the spin injection case, you have ferromagnetic. In the ferromagnetic, PJ is big enough, we introduce this term. In the spin Hall effect and spin magneto-resistance, we talk about flattening, so PJ basically is 0. So we don't have that. Okay. And then the third term is the inverse spin Hall effect. And inverse spin Hall effect is small because of this gamma, a small number. We call this spin Hall angle. It's typically less than 0%. Okay. So when we have a spin injection, so which means that this term is quite significant, and so we don't have to worry about spin Hall effect or inverse spin. All right. Now let's look at spin current. Again, this is a spin polarized charge current and inverse spin Hall effect. Then this is a gradient of the spin polarization. We can see that we normally we can keep all of them, which is not really a big deal. And this term in SMR theory, in the spin Hall magneto-resistance theory, they don't really they all I mean, in all of this theory, the first and second term are but in the spin injection case, again, because of the current is quite significant because of the spin polarized charge current, so the spin Hall effect can be ignored. All right, so as in summary, which is not a surprise, right? Depending on the cases, which term is more important, when we write the formula or equation to describe the physical process, we don't have to introduce all of them. We just have to introduce the most important. To conclude, the equation of spin and charge transport has been reviewed for the 3 processes. Now we have a unified picture that can describe all of them.